Passive House 101 series, the show where we try to make it accessible for everyone to get into Passive House. My name is Jose, and I'll be your host for the next hour. And today, our presentation is about continuous installation, which I think is one of those topics that really get people interested because it's one of the complicated ones to figure out. And a little bit of an intro on Kevin. He's the co-owner of Brennan and Brennan Installation and Airtightness, firefighter with the New York City Fire Department, and the co-host of Passive House Accelerator's popular construction tech program. He also teaches the Passive House tradesperson course, in case any of you is interested on learning more about how to apply all of these pieces of information in the field. And well, with that said, I'll just cede the floor to Kevin to take it away.
Thank you, Jose. I appreciate it. All right. So I'm Kevin Brennan, Brennan Installation and Airtightness. I'm a proud Passive House tradesperson. I was about 8-10 years ago, I was brought in as a trainer, and I was teaching air sealing and insulation for a weatherization training company. And we discovered Passive House, and you know, it's the basic building blocks of building science, continuous insulation, airtightness. But what Passive House does is just brings it to the next level. So the topic we're going to talk about today is continuous insulation, and the continuous insulation is one of the keys to making buildings work, and we focus on it in Passive House. And I'll take it down a little bit of a storyline, and we'll go from there. So as I was preparing for this presentation, I asked myself, I said, what kind of relationship do people have normally with insulation? You know, like, and then I thought about it when I was growing up. This is the house I grew up in. I'm in Staten Island. It's located, you know, kind of near the water. Originally, it was a summer home, and then when in the 70s, 80s, when Staten Island became more of a permanent residence from people leaving outside the city, became more of a permanent residence. But this was once just a summertime home. So this is known as a bungalow, the construction type, or arts and craft type of bungalow. What you see here in the front, what you see here in the front used to be a porch. So that was like an outdoor room, and then it was converted into a part of the living room. So this house was uninsulated. So it was just a wood frame, tongue and groove boards on the outside with some siding, some single pane windows. And over the years, as we grew up there, we lived in it. My brother and myself, my family, we made little improvements. So after my brother and myself got into the weatherization industry of doing air sealing and insulation, we insulated the walls with cellulose, and then eventually, as the story goes, we eventually added some exterior insulation. But we didn't have the knowledge of Passive House how to make this a super high performing home. We took it from a low performing home, quite leaky, house over a crawl space, you know, all the challenges that has, and we made it into a mediocre home and improved the boiler. So when I researched even further back, I was asking myself, well, what was my ancestors' original relationship with insulation? So this is a typical Irish cottage. My heritage is, according to Ancestry.com, is 88% Irish. Some people say I have the map of Ireland written all over my face. And somehow I get the sense of humor, and really the same sense of humor as Irish cab drivers. So that dry, witty humor sometimes comes through. But as far as this house goes, is what was my ancestors' original relationship with insulation? When you look at the walls being stucco, plastered on the inside, just rock, you know, pretty stone mass walls, there's really no insulation. But the waterproofing feature of the house, the thatch roof, is technically, when you think of it, is insulation. So that was the first roof insulation that you could put in a building. So it kept them dry, but it also, you know, as the house got heated, it kept some of that heat in from the chimney. So there was a way back when they were building thatch roofs was when we first had our relationship with insulation, because it kept those buildings a little warmer. And now we fast forward to modern times. This is in 2010, 2012, where Passive House is just starting to get rolling in New York City, and this is what is possible with continuous insulation. So this house here in the center is a Passive House known as Tight House. It's on Park Place in Brooklyn, and The blue is that it has an exterior insulation finishing system. So the outside is completely wrapped with insulation. The windows are R7 high performance windows, but compared to its neighbors on a 20-degree day, this building is not losing any heat. The neighbors next door, they're losing a lot of heat. That's all that red that's coming through there. So that's probably an uninsulated building. And the beautiful part of passive houses, when people see them and they experience them, they're comfortable, they're warm, they're cozy, is that they're kind of contagious, because this building over here is in the process of getting a high performance renovation at that time. There are no windows installed here. They're being replaced at that time. So I love this photo. It explained a lot of about Passive House and kind of like what my journey was. Ironically, when I took my first Passive House tradesperson training, it was with Julie, the architect of this project, and then shortly thereafter, Sam McAfee borrowed the infrared camera that I had access to and created this wonderful image, and I've seen it everywhere. So that's my quick little story of what was my original relationship with insulation. So let's talk about how insulation works. Insulation works by slowing heat loss or heat gain on the most basic part of trapping still air in small little pockets. So if you can imagine a vat of fiberglass, that it traps the air between air to glass to air to glass. So it's nice and fluffy, and it resists the heat going through it by keeping those little cracks there. They're trapped with air. And then if you do have insulation that's fibrous and air runs through it, it either increases the loss or decreases the loss. Sometimes we call that wind washing, or it has other effects, or convection in the loop. So basic in summertime, like the room I'm in now, the sun is beating down, and it's causing the roof to heat up, and we are cooling on the inside, and we're keeping the heat out and the cool in. So the path is just from hot to cold. So the pathway is from outside to inside. Then when we reverse that in wintertime, or based on our climate where you're located within the world, is that we have a warm zone on the inside, which is comfortable, say 70 degrees, and that's going to go from inside to outside. And where we separate our building is known as our thermal envelope, or our control layer, our thermal control layer. So that thermal boundary limits the heat flow between inside and outside, easily identified by the presence of insulation. Not always, sometimes you can't really tell. And then the location of the insulation in correlation to other components is critical. So we'll get later on in the presentation, we'll talk about vapor barriers, and some vapor barriers are air control layers. Normally you want your air control layer right up with your thermal control layer, or your thermal boundary. Another thing to point out is the evolution of insulation has come a long way. We've realized that there are many different ways to insulate, different products and how they work, and I'll try and touch on them of how they work. But something as small as 7% voyage can reduce the effective R value of that wall that's stuffed with insulation by up to 50%. So when you go to Home Depot and you buy a bag of insulation, it says R13 on it, you're only going to get R6.5 if you install it with just 7% mistakes. And that's not a lot. That's taking an exam and getting a 93 on it. If I get a 93 on an exam, I'm very happy with myself because I only got a few wrong. The basic criteria for Passive House, as you learned in the intro, is super insulation. That's what we're talking about today, is continuous insulation. The next one is thermal bridge free design, and that's a part of the insulation process, but it's also really technical. How do you attach things to buildings without having them be thermal bridge, but also structurally sound? A few different areas there. And then airtightness, 0.6 air change per hour, heat recovery, ventilation, and then the cooling demand, all built in the model. So the model is key to helping us figure out how much insulation we need. Rather than going down a prescriptive path where the code tells us exactly how much insulation we need, we're going to use an energy model. And that's what separates Passive House. So just a basic overview here of what continuous insulation is that this is from an image from the Department of Energy's Build America website. So this is probably 15, 20 years old. But the insulation board below the slab here is our first layer of insulation. It goes up and transitions to the outside. So the blue board on the outside is rigid foam board. This is a brick built building. And then we have a combination of continuous insulation outbound and 2x6 R19 fiberglass inside. So the thermal boundary is under slab, kind of like at the footer, and then up the wall. The window itself, depending on, all windows give some sort of insulation value, double pane, triple pane, and they are part of the insulation system. And then as you go up the wall to the top of the window head, the critical part here is the header, making sure that the header is insulated properly and continuous, because you can't have too much there. It looks probably have some spray foam there. And then the roof, a typical flat roof. The flat roof, you're insulating the parapet and the roof itself. So if I took instead of my red line, if it was my blue line, and I tried to draw it, the blue line for my insulation would come up all the way here, up to the top, all the way over and across the roof. So I have continuous insulation without any gaps. Very common in construction is that we'll have an uninsulated parapet, right? So that won't be insulated. Above the header, that will be uninsulated, or a break or gap or weakening in it. And at this slab here, we would have a break or a gap in the insulation. So it's very common in normal construction when we're not focusing on these details of how we would do it. So what are typical passive house R values and U values for walls? Because when we think of insulating walls, these are the most common ones found in passive house over the years. So first one is a EFIS masonry. It's a block wall with exterior insulation finishing system on the outside. That could be with EPS or right now we're doing it with mineral wool. And then this is ICF, insulated concrete forms. That's the image of the product on the intro, the first advertising slide. We have lightwood I-beams filled with insulation. We've got formwork expanded clay, not very common in the US here. This is aerated concrete with an exterior insulation finishing system. More common to our type of construction is a framed wall with insulation filled into it. We've got SIPs, we have vacuum insulated panels down here, and we have other. So these are kind of common to PHI and more common in Europe, but you can see that they're very thick, 10, 14 inches thick, or 12 to 15 inches thick. So they're thick, fat walls. And that's kind of based on the sweet spot of these single family, kind of like small residential homes within Europe, which is the first go. But as we increase the size of buildings and our surface area to volume ratio increases, it gets more favorable towards having a less insulation. But these are really common types of insulation in North America. So if I was just going to go laser pointy here, this is what I call fat wall, where it's exterior rock wool insulation on the outside, cavity insulation. So it's a combination of stuffed insulation and wrapped insulation. This is a rigid foam board product with cavity insulation, rigid foam board. One of my favorite ones is an I-joist. This is the I-joist here, and that's filled with most likely say cellulose, ICF, kind of like a commercial wall with steel studs and all exterior insulation. This is what Building Science Corp would call the perfect wall. We've got the double stud wall right here, double stud blown in with cellulose. The studs don't attach. It's a nice fat wall. The cellulose is rather an affordable type of insulation. Another version of the double stud down here. There are many, many different types of wall types that we can do here. And these wall types can go from wall types to roof types, and then sub slab would change just a little. All right. So when we talk about insulation, the difference between one type and the other, it's actually measured. It's measured in R value, and R value stands for the resistance. And R value in the units is BTUs per square foot per hour per degree Fahrenheit. So the formula is down here. And you can figure this out. So say you're a manufacturer of fiberglass, you send that product to a laboratory. They put it in a perfectly airtight chamber. They put heat on the bottom, and they put a temperature up top. They can measure the temperature difference that goes to it, and they give that a resistance value. The beautiful part is resistance values, they can easily be added. And a lot of times that's that center of the wall resistance value. So when I take the insulation out of the bag and I put R15 in the wall, that's only the center of the insulation. It's not my whole wall R value. These are the different types of insulation that we can have. The most common one when I was growing up was fiberglass bats. and fiberglass bats are 2.14. That's an R, 3.14. That's a R value per inch. So this is a 3.5 inch bat, and that's probably R11 or R13 right there. We also have my favorite product, which I started my career using, which is blown-in cellulose. Blown-in cellulose and an attic loose fill is what's showing here, and that's a 3.13. And then all these insulations that I'm talking about, the fibrous ones, they use the air as the insulator, and when they use the air as the insulator, the heat goes from air to fibers of glass, air to fibers of glass, so it's slowing it down. When it's going through cellulose, it goes from paper to air to paper to air to paper to air, paper to air. So the thicker it is, the harder the time the heat has to go through it. We also go down here to rock wool bats or mineral fiber bats. That's at 3.14. We also have we've got vermiculite down here, which is an older product, not really commonly used. Aerated concrete blocks, which I'm seeing more and more in my market in New York City here, that they're building the wall out of these aerated concrete blocks, and because the air is trapped in the concrete blocks, that's acting as insulation. And then we move into what I call the high performance, or a changing of moving away from air to a gas to insulate. So when we go to extruded polystyrene, or EPS, that's a rigid foam board. Those are the boards that are in there. So let me back up a second. EPS or polystyrene bands, they're boards that's like a coffee cup. They're at around R4 per inch. That uses air as an insulator. And then as we move up the chain of insulation, we start using little bubbles or little pockets of gas. So if you use the spray foam that this gentleman is spraying in the wall, those little gas bubbles, the blowing agent inside of the foam that's being created right there has little gas bubbles that resist heat even more than, say, air would. And then kind of on this chart here, the top of the food chain is the polyisocyanurate. That one has a high performance gas embedded into the foam that's there. So many different types. When I teach the class, the tradesperson class, I have all these samples out. It's a little bit of a show and tell. It's a good way to know how the product performs, why it performs, and what's actually as the insulator. So the example I'll give is if I took a bat insulation and I squished it completely, and there's no air and it's just going on all the glass, what's the R value of that? Is it very high or is it very low? There's no air, there's less air, so I reduce the R value. So one of the effects that you see here is that the voids in insulation, typical bats, this is what you get on the bag, the R19, and best practice is your performance of putting it in at 99, 98% correct is R13. And then with some small defects, you can see that the R value is reduced. So a 5% voids can reduce by up to 60%. So it's a process. So in order to do insulation, it should be installed as perfect as possible, and it should meet the wall type design. So this is from Home Depot's website. Home Depot's website, these are the codes, these are the climates that are down here. And you can see that for 2x4 walls, it's for my climate, it's R13 to R15. And then for 2x6, it's R19 to R21. Now, as you go up in your code cycle, there's also a requirement or an add-on that gives you CI, continuous insulation. So we'll touch on that a little later. So this is the most common wall type that I am installing, or kind of a version of it that we're installing. It's a dense packed wall filled with cellulose. I like cellulose because I'm able to put it in the wall. It's able to be installed perfectly by the machine. It's filling the whole cavity in place, as opposed to me putting it in the wall and trying to fluff it and make it perfect. And you can see that the studs are not connected. That's eliminating the thermal bridge. And this is the air vapor barrier. The vapor barrier will control how much vapor gets in the wall. So talking with R value and insulation is that when we show these thermal imaging pictures, what you're seeing here is a standard wall with fiberglass bats in the wall, and you can see that all these studs are showing up cold. That's because it's a conductor of heat from inside to go to outside. So then the studs get cold. So that's known as a thermal bridge. And that thermal bridge, how would you eliminate that thermal bridge on the outside when I stuffed in between the walls with fiberglass, is that I would put a board insulation on the outside to minimize or stop that wall there. So if I was, for example, to take all these studs and slide them over, that wall would probably have around 15% studs. So 15% of this wall is all studs, and 85% of it is actually fiberglass and sheetrock and things like that. So there's different form, and then we'll talk about the whole wall R value. This is an example of a balcony acting as a thermal bridge. The balcony needs to be supported in structure, but you can see the heat loss that happens there. So how do you make that connection with being balcony and strong there? Is there a way? And that's where we find Passive House. We're calculating all those little thermal bridges, and they're adding up. And there are ways to eliminate that balcony thermal bridge that might be there. So this is just an example of how we analyze thermal bridges. Thermal bridges are analyzed in modeling software, a Flixo or Therm, and it's just helping us to understand how the heat is flowing with a little bit of science, a little bit of calculation. So these isotherms are nice and spread apart, meaning that they're not touching. And you can see here that these isotherms are coming through and they're getting a little squeezed right here because they're decently spaced, and you can see that there's a block insulation. And this is how you would analyze it. This would be the base detail, not flowing too bad, but there's a little bit of heat loss here, and then this is how you would improve it. So it's analyze and improve. All right, so just like me sweating here, condensation is what kind of makes or breaks insulated walls. Way back when we first started insulating buildings, we would notice that condensation would develop on the walls themselves. And this is kind of what happens when you have high humidity and condensation. You could see that the studs are all marked by their fasteners, and where the actual moisture is actually condensing and getting wet is on the studs, on the fasteners, and at the thermal bridge at the top and the corners, and it's kind of down low. So this is high humidity with really cold studs or to the outside. And what would happen here is that somebody might get sick from mold, or this is kind of like the worst case scenario. And how do you eliminate this or you reduce this is by having a higher R value surface that can allow the vapor, the moisture, to actually go through the wall. So rather than trapping it in, and you give it a flow path, the moisture in the air wants to go from high concentration to low concentration and wants to get out. So what's happening in that wall is that the moisture is hitting a point at the dew point and it's condensing. So it's going from a gas to a liquid, and it's condensing on that surface. It's making it wet, and anything that's wet for a long time will dry out. So what I'm showing here is one of the classes I teach for the Air Barrier Association is that this is a typical peel and stick membrane, and that peel and stick membrane is vapor closed. It won't allow vapor to go through it. So this is just a simple chemistry beaker, and the water is kind of like slightly boiling. And you can see that with the disc on top that's glass, that there's no condensation coming through. Whereas on this beaker, that is a vapor permeable membrane, and that allows the vapor to go through it, and you're able to see it as it's condensing on the glass disc that's there. This same process could work if I took a piece of insulation. So if I took rigid foam board and put it on top of the assembly that I'm putting together, which is a vapor closed peel and stick, and the EPS, no vapor would go through it. Whereas on this one, if I took rock wool board and put it on the outside of the wall, I would still see that condensation there because the vapors have the ability to go through the rock wool, which is called a vapor open assembly. This is a project that I worked on in Brooklyn, one of Mike's projects. We chose this wood fiber board on the outside of this project because previous renovations on this project had spray foam in the walls. So it's a wood frame building. They put spray foam in between the studs, and spray foam is vapor closed cell spray foam. So the moisture cannot go through the insulation. So if any moisture got trapped in that wall, we wanted to give it the ability to go through the wood sheathing on the outside, and then also be able to go through the insulation. And this is what that house looks like now. You can't even tell it apart from its neighbors. There's a rain screen system put on there so that any vapors that go through the wall will then drain out as a gas. So there's an airspace behind here. And one of the nice parts of this is that they totally took down the porch so they can get full thickness at this band of insulation of this band here, which would normally be a weak point in the house. That's just one example of the work that I've worked on, the projects of a vapor open assembly. I think that's it, Jose. My name is Kevin Brennan, Brennan Insulation and Airtightness. I'm here to answer any questions you may have and try and do my best to take on these difficult topics. And please let me know if there's anything I can do with to help out. All right.
Yeah, thank you. Thank you, Kevin. Great presentation. A lot of good information there that I would like to comment on, but I know we are a little bit tight on time. I know you have to
No,
you
yeah,
have to move away from the meeting, or
no, you're
you have
fine.
time?
Yeah.
Great. My main question is actually about the condensation on the wall. That's been kind of a topic, thinking about insulation continuously, and then the air tightness and the thermal bridges. Do you have any best practices for if at some point during your practice you identify that your detail is great, you don't have any problems in terms of how to build it and R values and all that, but your condensation shows up within the wall cavity inside the building? Do you have any specific membranes or tapes or seal methods that allow you to remain airtight but allow the moisture to go out of that assembly?
Yeah, so anytime I'm working on assembly, I try and make it vapor open, meaning that vapor can move in both directions. And I'm in New York City, so we're a heating climate, but we just have pretty much a lot of cooling days too. So climate dependent is also there. But my preferred preference is that I have an insulation product that moisture can go through it, then a water control layer that also can allow the vapor to go through as well. And then a lot of times the project working on has that kind of like sandwich or fat wall kind of system where the cavities filled with insulation, and then there'll be like a board product on the outside. I like to stick with the wood fibers or the rock wools that will allow the moisture to go through it. That's my preferred method. And then as you insulate a wall, you're reducing the inside surface temperature from getting colder, and then you're reducing the chances that those condensation, mildew, mold points could possibly happen. So,
Yeah, no, I think those are great recommendations. And maybe this is a topic for another 101 once we go beyond the 5 basic principles and go into the more nitty-gritty of it. But we're going to go to the questions. But before that, we'll give it out to the sponsors. Kim?
Hi, I'd like to give a big thank you to the fine organizations that make our work at Passive House Accelerator possible. First, a big shout out to our stakeholder partner, NYSERDA, the New York State Energy Research and Development Authority. Thank you, too, to our founding sponsors, 475 High Performance Building Supply, Baxt Ingui Architects, Glavel, Minutair, Mitsubishi Electric Train HVAC US, Partel, Rockwell North America, Stocorp, and Zola Windows. And thank you to our champion sponsors, Bewiso, Icon Windows and Doors, Intelligent Membranes, Proseco, and Source 2050. And thank you to our patron sponsors, Brennan, Coltraco Ultrasonics, Euroline Windows, Holstrom System, Inotech Windows and Doors, Lamelux, Owens Corning, RDH Building Science, Sanderson Sustainable Design, and US Engineered Wood T-Stud. Thank you, sponsors.
All right. Thank you, sponsors, for sure. Thank you, Kevin. So we can move into questions now. And I know that up first we have David Majkowski. If he's on, you can go ahead with your question. Or
yeah,
your comments, actually.
Yeah. Yeah, thank you for taking that. Just curious on, and a lot of the comments have said this, that really poor performing windows or old windows, single pane windows seem to be, are they a huge part of the current leakage and energy performance of these buildings, that as an area that can really move the needle if you're trying to get to a passive house and higher performance? Is that one of the bigger levers to pull?
Yeah, single pane windows are not helping your cause when you're trying to save some energy. My general rule of thumb is giving advice to friends and family members is to purchase the best product that you can afford at the time. So if you're going to need new windows, if it's the front facade, rear facade, or you're going to do them all at once, buy the best ones that you can afford, and the ones that'll perform not for today but for tomorrow. So if you can afford a triple pane window, it'll help you to tag on your insulation processes. So if my house, for example, I have a plan of replacing my double pane windows with triple pane windows when I do the facade. And when you do the facade reside or redo the EFIS, it's a great time to do your windows, and then that gives you the option of adding exterior insulation. And that exterior insulation, we really want to be modeling it to know how much is too much and how much we need. But the windows are a part of that whole wall R value. One of the things I didn't put in the slides because it's a little high tech is that I take an R19 wall with R3 windows, and I average the 20% glass. Now I have an R7 wall roughly, that's there, because it's the whole wall average R value that really matters. But if I had an R7 window, now the whole wall R value would be much, much higher at 20%. So I hope I answered the question, but windows are a key component.
Great. Thank you.
Thank you.
Up next with Craig Handy.
Hi there. When I was doing my Passive House training, there was a comment that using spray foam as an air barrier is sort of discounted, not really considered an effective long-term air barrier. And I've been I work with a lot of architects who are quite comfortable with using spray foam as an air barrier. And I've been looking online for a debate and some substance on whether it does function as an air barrier or not, and just can't find any substance, one side or the other, that argument. I'm curious, you want to weigh in on that?
I can attempt to weigh in on it. So depending on how you're using the spray foam will depend on its performance. So when you're stuffing it in between the studs, now it goes spray foam, which is airtight, connected to a wood stud, which is not airtight. And it all depends on that seal that goes between the stud and the spray foam. So depending on how the house is moving, the quality of the spray foam, it could compromise that. A good way to use spray foam in the commercial aspect in it, industrial or schools, is a continuous spray foam outside. So you would do all your transition membranes with peel and sticks, and then you would do insulation outbound, and that would be a part of your air barrier system. So that is a good use of it. Very common in Canada to use the spray foam in that area. There is ABAA certified spray foam that the manufacturers go through the process, and then you're buying the whole system, the peel and sticks. So it has to be an air barrier system, and it can be done. It's just when typical architects designing residential homes, they're only shooting for less than 3 air changes per hour. Whereas within Passive House, we're going from much, much lower at 0.6. Our tolerance is tighter, so we don't really rely on the spray foam for that level of air tightness right now. It can be done, but it really takes a lot of quality assurance and managing the details. But the devil's in the detail for everything. So I personally use spray foam all the time on projects in tricky areas where I want to fill the gap between, the first stud of the joist, and I want to make sure I get a lot of insulation in that vulnerable joint. So I'm not an anti-spray foam person at all. It's just the right product has the right place, and I'm using it for its high R value in a limited space. And I'm also using it to plug the hole, but I'm not using it as a whole air barrier system.
Yeah, that's my feeling, is that a proper membrane air barrier is probably an important part of using spray foam.
And managing your details, your drywall, you do an airtight drywall, what's your roof line, there's a lot of things that go into airtightness that's not very, very clear. Cool, thank you.
Yeah, the devil is in the details for sure, especially with Passive House. Up next, we have George Nogles. I hope I said that right.
Thank you. We have the Thomas fire. Are you able to hear me okay?
Yeah, go ahead.
Here in Ventura, California, we had the Thomas fire. And after the Thomas fire, I went up and visited the structures that had burned. I noticed a very strong headache after doing that. And I think the reason was dioxins related to partial combustion or complete combustion of plastics. I guess partial combustion would be more accurate. So I'm just wondering, of the membrane and insulation materials that you mentioned, which of those materials are going to produce or not produce dioxins in a house fire, please?
So me as a New York City fireman, the dynamics of fire are something I deal with every day. But what we're seeing in the world as climate change is happening and things are happening and buildings are being sprinklered is that the most common fire starts inside of a building and then goes to the outside and the building burns down. But with sprinklers, we're getting buildings that get knocked down with a sprinkler and don't go through the full process, and the fire departments come and put it out. But our biggest hazard now is that the fire on the outside is going to burn the outside of our buildings and then go to the inside eventually. As far as which products are fire retardant, the mineral wool products are fire retardant, or they reduce how much fire. So my preferred wildland fire wall assembly is always a rock wool board on the outside. The denser, the better, and then rock wool insulation or rock-wool insulation in between the studs. I prefer to blow rock wool in the cavity; it installs a little easier. And as far as like the rain screen, you know, if you could do like a cement siding on the outside that doesn't have the same capacity to burn, gives you some fire resilience that's there. And then no matter what you put in your house these days, if it's plastic based, it's petroleum based, it's going to burn, and it's going to burn as a plastic. The toxic gases are going to be a lot more. It's going to give you those headaches. And anything that's plastic based is also emanating VOCs and other things like that. So what we put in our homes is important too. We have gone from legacy homes where things were made of wood and cotton and standard fabrics to modern day homes with plastic televisions, foam insulation couches, and different things like that. But it is a challenge, but the dynamics of it are changing. So if I had my preferred assembly, I would like to make as many fire resistant buildings as I can. Just sometimes price gets put in that category too, because those denser those products are, the more the materials cost. Did I answer the question? Did I miss anything?
I think you were spot on what he was asking, actually.
Thank you.
Yeah, there you go. Up next, we have Caitlin Holmes.
I think my question was just very similar to the one that was just addressed. It's really just looking at the trade-offs of this material selection in the event of fire.
Yeah, your material selection is important. There are some benefits to each insulation type, but most projects, when you look at how they're designed based on code, you're going to have a sheetrock wall kind of as your main fire block. So what's in the wall is not really supposed to burn for almost an hour or 2 hours based on what's there. So, but what your risk tolerance is and what you're putting in your house could change. You know, like me as a cellulose installer, cellulose can smolder, but it doesn't actively burn. And then when it's packed in there really tight, it doesn't really allow for a lot of air to go into it, so it doesn't burn. So I've been to quite a few H-type fires. They're tenement fires where the cellulose in the ceiling prevented the whole roof from going up. Whereas if it was a different insulation product, the more air that flows through it, the greater the heat can travel. But the cellulose smoldering would be in there. It would be a better assembly if there was no air, and then the fire didn't have a path to travel. But I can nerd out on this all day, but I don't want to bore anyone.
Yeah, no, that's okay, Kevin. I think that's a really important question to really ask and get some context on. And I think the answer is what you're saying. You know, try to find the best material that you can get, or I guess try to put some of the good budget into those materials if you're in a place that is going to be prone for fire or something that could be a hazard to the property. You know, overall, especially now thinking about insurance and everything else. And yeah, I guess I could also nerd on that. And get a little bit into the economics of why it's important, but it's always good to just pick the right materials for the place you're living in, for sure. But up next, we'll continue with Jacob and his question.
Yeah, hi guys. I was just kind of wondering what your thoughts are on a cladding attachment system regarding the transition from the wall, whatever insulation you're using, and just kind of what your thoughts are on that.
Yeah, there's some great research out there by RDH. They did a full thermal analysis of all the cladding attachments. They categorized them. They gave them chi values for each one. So there are a lot of great options out there. If you're using green girts or whatever kind of like fiberglass clips, they're all great. There's many ways that you can do these cladding attachments. What you want to move away from a science-based approach is those, something that creates a greater thermal bridge than what's there. So we're super insulating these buildings on the outside. We don't want to just take a Z-girt and then wrap it around the building every 16 on center. So we want to prevent making it into a radiator and increasing the heat loss. We want to make it less. So what's going on there. So there are thermally broken clips. The systems are designed and tested, and you get some numbers on them. And that's the beauty of Passive House, is that we're looking at those finite little heat losses that are really adding up, and that helps us to analyze, to then make smart decisions, as opposed to just doing it because that's how they did it back in the day. Like we're using a little bit of science, technique, and technology, the T's of construction tech that really helped us make better buildings.
Yeah, thank you. And just as a follow-up with that, with the fire conversation that we just had, I was noticing as well that some of these cladding attachment systems actually are fire rated in some capacity, at least. Again, just kind of, instead of making 1,000 holes in the wall, these cladding attachments really are something that I think are not looked at enough.
Yeah, we've come a long way from when I first started working in Passive House, analyzing cladding attachments, to now there's an entire association, RAINA, the Rain Screen Association, that's doing great work.
Yep. Great.
So,
thanks, guys.
Thank you.
Yeah, thank you, Jacob. We have a good amount of questions. So I think, Kim, do you think we can take one more question and then run the sponsors and then we keep going? Do you think you have enough time?
Yeah, why don't we go to Enrique and then we'll do a quick event announcement. How's that sound?
All right, let's city to Enrique.
Yeah, hi, Jose, how are you doing? Thank you, Kevin. This was a great presentation. This is an extension of George and Kathleen question regarding climate-related events. And this is regarding flooding. What kind of strategy would you suggest or is being thought about the envelope to make the envelope more resilient to flooding?
So ironically, the house I showed you that I grew up in was flooded during Sandy because it was by the water. So we not only got to renovate it once, but we also got to renovate it twice. And in that project, because it was a wood frame building over a crawl space, the second time around, we decided to do spray foam up the wall in the cavity, closed cell spray foam that would absorb moisture up to around 4 feet. And then we put up our kind of like gypsum faced sheetrock, so no paper, so that if it ever does get flooded again, we're just gonna, like, we don't own the building anymore. My brother did that renovation. My parents don't live there anymore, but that was our strategy there, that we use an insulation product that can't absorb the moisture, doesn't have the possibility to, and then that has the ability to dry really well. That's one of the strategies. Some people, there's plenty of different flood resiliency strategies that are out there, but a lot of the times, even though you get flooded, you're still going to have to take down the drywall, dry out the wood frame or whatever it might be. So just use smart materials when making those decisions.
So there would be the foam on the outside.
Foam on the outside and foam inside the cavity walls too.
On up to 4 feet.
Roughly, yeah, because that house where it was right at 4 feet for Sandy. That was the decision we made.
Yeah.
And a lot of those houses were mandated, not in that neighborhood in particular, but in lower lying areas. They wanted to raise those houses up on pillars But design for not today, but for tomorrow's climate is important.
Okay, thank you much.
Thank you.
For sure. And up next, we're gonna go with Thatch Carrick. It's still on.
Yeah, I'm
Hey,
sorry.
still on.
So my question relates to, so when you're retrofitting a house for passive house standards, but you're working with a brick home and they're typically made so that they can breathe. We're actually in that situation right now, my partner and I. And so the big strategy we're going with is making sure all of our additions meet passive house standards. But we're kind of unsure how to deal with the existing old brick walls from the 1940s.
So the brick walls have plaster on them, or how are they? Are they cavity walls?
So we haven't dug in too deeply, but it's a solid brick, and then there's like some type of like plaster and slat over it, but there's no like actual insulation or anything.
Yeah, it's very common for brownstones, masonry buildings. Kind of the approach that we take in our retrofits, the brownstones that we work on is if you're gonna demo and take the plaster off, just take it all the way down and then kind of treat the brick if it needs to be pointed. And we install a fluid applied air barrier at that point to do air tightness, but also water tightness to make sure that water doesn't come in from the outside to the inside. And then we frame a wall that's 1 inch off the wall, and we then insulate that wall. And then we'll use a vapor barrier, vapor intelligent membrane, Intello, or a Segas product, or Rotoblas, or anyone that has a vapor kind of like intelligent membrane. So
Awesome.
and then that would be insulated. What's that?
Oh no, I said thank you so much, because that's something we're struggling with.
The other thing to think of, it's on the project working on 25th Street, is that if you were doing an exterior renovation, you could do a rock wool based EIFS system and then not have to disturb the inside. So a big fat rock wool based EIFS system on the outside, and then it looks like stucco. And now you don't even have to, your air barrier goes on the outside, air control layer. All the vapors can then go through the wall, and it can go through the air barrier. It can also go through the insulation and through the stucco that's on the outside. So great opportunity there. And then rocks don't burn, so the outside of the building is now protected by stucco and rock wool. So it's a good design solution.
Thank you.
Thank you both. Up next, Mike Weiss.
Hi, thanks, Kevin. This has been great. A question for you. I'm in a multifamily New York City building and just sort of want to get a baseline for the R value of a 3-width brick wall, masonry brick wall. Just so we can figure out how much the R values being added with the EPS system. So do you, do you have a standard number for an R value?
I'd have to look it up, but I think it's about an R.5 per inch, I guess you could say. So if it's a true 12-inch 3-white brick wall, you're probably in the R4, R3 area or so. But it's always best to analyze and to go through. So when the Passive House consulting is kind of like figuring out what your wall makeup is and how you're going to do it, they actually measure each one of those and they put it into a model. The Passive House consultant I work with, building type on the projects I work on, the details that they put out are phenomenal. The amount of thermal analysis that goes in for thermal bridging, also R value design, and then even sometimes they'll do a hydrothermal analysis on the wall to see where the cold spots might be, where there's condensation risk, and they do a great job. But it can be analyzed. But as far as a New York City typical building, it's around the current R values, probably around R3 or R4. So
okay. And one other or two other points, I guess. Like it looks like DOB in New York City now, at least for multifamily buildings, they're requiring non-combustible insulation around the fenestrations. If you're using like an EPS sort of in the field, you still have to kind of ring the fenestrations with a non-combustible, like I guess a rock wool. I wonder if you can speak to that. And then the other thing is just insurance and contractors who are doing overclad insulation. Like it seems like it's very hard or very expensive for contractors to get insurance.
Insurance is always difficult. Trying to figure out where you fit in. Having whatever insurance broker you're using is understanding the business that you're in. You know, like I have a hard time with my insurances. I'm not a roofer. I'm an insulator. I'm working inside 90% of the time. So my fall hazards are less, my other risks are there. So that's always a challenge. But when you move to the outside working on scaffolding, there are greater risks on the outside there. So my insurance might be difficult, but there are tons of restoration contractors throughout the city that are doing great work renovating these buildings. We could use in Passive House a little more because I see overclads happening and I see really thin insulation. And I'm like, that's a 25, 50-year decision. And you went with the minimum, you didn't go with the maximum. So it kind of pains me, or you didn't figure out your details to the best, you know, like, or you left the windows in, you should have done the windows, pushed them out into the envelope, would have been a much better design. You know, you're putting that scaffolding up, really doing a deep energy retrofit or deep retrofit of the building would be great. And then as far as the New York City Department of Buildings and their flammable, fire resistant exterior, non-combustible insulation on the outside, makes a lot of sense. Fire stops in other areas. We are a reactive organization. You know, fire department, buildings department wait for the tragedy to happen, and they're really looking at Grenfell Tower in London of like what happened there. You know, like how can we improve and make sure things like that don't happen again. There are ways of doing details that make sense. You know, the beauty of Passive House is that it's a European energy system that we just kind of adopting it over here because a building in Europe has the same physics, same environments that it is there. It's just the details and the culture that we're building in are slightly different. So when we run it up the, when we run it across the pond, it's just the same details. And across the pond, they use details above the heads of the windows. Like you can see in my background, if a fire is in this room, it's going to go up and out the window. And having details that are non-flammable on there are really good details because it buys you some time. And you let us do our job of getting in there and putting it out. But we can't, you know, things do happen. And, you know, we are a reactive society, but I think non-flammable exterior insulation products are the future. You know, what we're doing to achieve a non-flammable, non-fire, you know, risk is great. But,
thanks very much.
Thank you.
Yeah, thanks, Kevin. So there's a couple that have left the call. Right now we have someone that's just called Zoom user, but I'm guessing they didn't have a name. Maybe
I hate to cut it short, Jose, but I have a hard stop right now. I can see, so I'd love.
Oh, okay.
I appreciate you guys. Sorry.
No problem. So if you have a hard stop, then I guess we'll call it a day today, and we'll see you guys on the next events.
Great. Thank you very much.